All right, now let's talk about moles in chemistry. Okay, so moles is basically the central unit of chemistry. It allows us to do a bunch of different sorts of calculations and figure out different things. Some of those things are like, for example, the number of atoms and or molecules that we would have in a given amount of grams of a substance, the volume of a gas at STP, which is like standard temperature and pressure, and also it relates to things like if we have a concentration of something like the molarity, we can use it to figure out how many moles we have and how many grams and how much of a powder or like whatever substance we're trying to make do we need and or dissolve. It also helps us figure out what will run out first in a reaction by the limiting or excess and or all of like those sorts of things. So it's a very important concept and it comes up over and over again. So basically 1 mole of something, it's just a unit of measurement. Like 1 mole is equal to this number of atoms or molecules. So 1 mole is equal to 6.02 times 10 to the 23 atoms or molecules. And this comes from Avogadro's number, who is the scientist who discovered this. And it's basically saying that 1 mole is this number of things, like 6.02 times 10 to the 23. It could be atoms, it could be potatoes, it could be whatever. It's just like how we say 1 kilogram is equal to 1,000 grams. Same concept, or like 2.54 pounds is a kilogram or whatever. It's just like the standard unit. So now let's talk about how we can use moles to do calculations. So one easy way to remember this is that you're always going to multiply down from moles, and you're always going to divide up to get to moles. So what do I mean by that? So let's say if we're at moles and we're trying to get to number of atoms and molecules, we are going to multiply our way down. So we're going to multiply by Avogadro's number. So if we're at moles and we're trying to figure out the volume of a gas at STP, then we're going to multiply, and we're going to multiply by 22.4, which is like how many liters of gas there are at in STP, so standard temperature and pressure. And if we're at moles and we're trying to figure out how many grams of something or the substance that we have, we are going to multiply, but we're going to multiply by the molar mass. And if we are trying to get to moles, if we're already figured out or we're given how many atoms or molecules we have and we're trying to get to moles, we are going to divide. So we are going to divide by 6.02 times 10 to the 23. If we're at the volume of gas at STP and we're trying to figure out how many moles, we would divide by 22.4. And if we're at the grams of something and we're trying to figure out how many moles we have, we would, this is a typo, we would, it should be, multiply, divide. So yeah, if we're at grams, we would divide by the molar mass. And yeah, multiply down, divide up. So now let's try some examples. Also, just a key point is that if you're at grams for say, and you're trying to get to number of atoms or molecules, you would have to go to moles first and then do the conversion. There's no way to go directly there. Okay, so let's try these examples. Calculate the number of moles of 39 grams of potassium. So if you look at potassium on the periodic table, it has a molecular weight of roughly 39 grams per mole. So what that tells us is the molar mass on the periodic table, if you were to weigh 6.02 times 10 to the 23 grams, or 23 atoms of potassium, and you put them on a scale, the scale would read 39 grams. And just for context, 10 to the 23, very, very large number, right? 1 billion is 10 to the 6. 1 million is 10 to the 6. 1 billion, so million, and then billion, and so on, right? Trillion, 10 to the 12, whatever. So think about how big that number actually is, because atoms, again, are very, very small. So, yeah. So 1 mole, or 6.02 times 10 to the 23 atoms, would weigh 39 grams. So, now if we have to figure out the number of moles, we would start off by writing 39 grams, is what we started with. And then the way you would do this is you would put 1 mole on top, and then the molecular mass, so the periodic table, because these are interchangeable, right? They're equal to each other, so we can flip them. It would be 39 grams. This is from the periodic table, molar mass. And then you can cancel the grams, and you're left with just 1 mole. So that makes sense, right? Because that's what the periodic table tells us. That 39 grams would be 1 mole. Okay, now if we have to figure out how many atoms are in 39 grams of potassium, we would start at 39 grams potassium, multiply by a 1 mole on the top, and then 39 grams per mole. So conversion factor, so that way the grams have now canceled and we're at moles, and we multiply by the fact how there are 6.02 times 10 to the 23 atoms in 1 mole. So it's just conversion factor. So when we do that, we'll see the moles cancel, and we're left with just 6.02 times 10 to the 20 atoms. Okay. Let's try this one. So calculate number of molecules in 80 grams of calcium, and we'll say the molar mass for calcium on the periodic table is roughly 40 grams per mole. So 1 mole is 40 grams. So number of molecules, so let's realize where we are. So we're given the grams, and then we got to get to number of atoms and molecules. So we got to go to moles and then down, right? So see how it's like the central unit? It allows us to do conversions. So we know that we divide by the molar mass to go up, and then multiply to go down by the Avogadro's number. So we would take 80 grams from the question that's given, multiply by, try to figure out how many moles there are. So 1 mole over periodic table mass of 40 grams for calcium in each mole. So it's 6.02 times 10 to the 23 atoms of calcium. It would weigh 40 grams. And then multiply by Avogadro's number. Per mole. And then when you punch that in, it's just going to be 80 and 40 can cancel to be 2 moles of cancel. It's just going to be 2 times 6.02 times 10 to the 23, which is like 12.04 times 10 to the 23. Okay. Okay, now let's try these ones. So volume of 40 grams of neon gas at STP. So neon gas, let's say the mass is 20 grams per mole. And let's try to figure out where we're at. So we have the grams, and we're trying to find the volume. So we're going to go grams, moles, and then down, right? So we're going to divide by the molar mass from the periodic table, and then use that, and then multiply by the 22.4 gas constant. So 40 grams that we started with times by 1 mole on the top, 20 grams per mole from the periodic table, and then multiply by 22.4 liters per mole, 1 mole. So then moles cancel, grams cancel, and we're just left with liters in our answer. So it's basically going to be 2 times 22.4, which is 44.8. Okay, now let's try this one. Calculate number of molecules in 5 liters of a gas that's at STP. Okay, so this one, we're at STP, so standard temperature pressure. So we know that 5 liters, and let me just kind of use this for you. We know that when we're at volume of a gas, we can use the conversion factor 22.4. So we're going to divide to get to moles, and then multiply to figure out how many atoms or molecules we have by using Avogadro's number. So 5 liters times 1 mole, 22.4 liters of a gas in 1 mole. So the liters can cancel. You're at moles, and then you just multiply it by Avogadro's number. Atoms per mole. So then the moles have canceled. Okay, and then you would get some number. You would get 1.34 times 10 to the 23. And if you're using sig figs, then just put 1 sig fig, so it's just 1 times 10 to the 23. But for now, don't worry about that. And then let's try this one. So how much would 6.02 times 10 to the 23 atoms of uranium weigh? So whenever it's a weight question, you're going to go, and you're given number of atoms. So you got to go to here, to moles, and then you got to go from moles to the grams. So we're going to divide by Avogadro's number on the way up, and then multiply by the molar mass on the way down. And for uranium, element number 92, the molar mass is 238 grams. Grams per mole. So we're going to take 6.02 times 10 to the 23 atoms, multiply by 1 mole on the top, and we know 1 mole has 6.02 times 10 to the 23 atoms. So now the atoms have canceled, and then we would multiply by the molar mass of uranium, which is 238. So 238 grams per mole. So the moles cancel. And then you're going to see that this is just going to be 238 grams. And that's our answer. Which makes sense because we know that 1 mole is 6.02 times 10 to the 23, and the mass on the periodic table is representing the mass of 1 mole, or 6.02 times 10 to the 23 atoms.